Anyway, so today we will discuss mainly about the procedure and the background theory of the V3F, or this is in colloquial term, this is called V3F drive, or variable voltage, variable frequency drive. So this is applicable for not only induction motor. One second. Not only for induction motor, this is applicable mainly for most of the AC machines, AC motors, I would say. This is applicable for synchronous, okay, synchronous motors also. Okay. So let's discuss for the induction motor mainly for this class. The electromagnetic torque for the induction motor, that is given by oops, equals to the air gap power divided by the synchronous speed in radian per second. Now the air gap power, if you remember, uh, that is equals to 3. Okay, let me write this way. This is the air gap power, and one by now omega is synchronous speed, as you know, is given by twice by stator frequency. Usually that is represented by F1. If you remember, for the equivalent circuit for the of the induction motor, stator frequency is represented by F1 or Fs. Rotor frequency is represented, because rotor frequency and stator frequency are different, so they are represented by different terms or different letters, word letterings. Okay. And this, of course, the frequency, because here this omega is expressed in mechanical radian or mechanical speed, so that is to be divided by the number of poles here. So if we put that in this equation, so this becomes here 3 square per 2 divided by twice by f1 in divided, and this divided by the number of poles divided by the slip. Now here this current, the I2 is the rotor current and R2 is the rotor resistance, of course, rotor standstill resistance, and these are all stator referred. Now it does not matter whether this is stator referred or actual rotor quantity, because there the when the rotor the resistance when referred to the stator, that need to be multiplied by n1 by n2 square, that is the turns ratio of stator and rotor, and I2 is to be multiplied by the n2 by n1 square. So that means the turns ratio involved in the current and turns ratio involved in the resistance, they cancel each other. Okay, so sorry, in effect the numerator remains same, whether that is stator referred or the actual value. So you can consider any one of them, that does not make any difference. Now okay, so let me keep here the equivalent circuit. So here we have the induced EMF, that is E1 to dash, and rest this is R1 L1. Now what is the current I2? Current. So if we put that in the torque expression, expression becomes constant. Then we have R2 divided by, then we have the current. Now, once again, in the last part, I have for the initial case, while determining the current, I used the dash notation. However, in the next part, you can use the dash notation or you can remove that, because it does not matter whether you are using the referred value or not. That the turns ratio in the numerator and the turns ratio in the denominator cancel each other. Now, let's restrict ourselves into a special case where the sleep is very small. So if sleep S is small, in that case we can write R2 by S is greater than this omega 1 L2. However, once again, if we put the square here, square of the left hand side and the square of the right hand side, this becomes much greater than the right hand, greater than the right hand side. So in effect, we can neglect the part here in the denominator, this part. So if we do that, the torque becomes, electromagnetic torque becomes thrice P by twice pi, because E2 square and U1 square, the E2 square referred and U1 square are same, so we can write this way also. So R2 square to a square, or this is equals to a constant part, then SF1. So this part is a constant by itself. This, if we can maintain a constant, in that case, the torque could be proportional to this term, which is nothing but slip into the frequency, which is once again proportional to the synchronous speed. So, or in effect, s into the slip into the synchronous speed is the slip speed. So torque become proportional if we can maintain the part in the third bracket to be constant. So in that case, we can write torque is proportional to SF1, or that is proportional to S into the synchronous speed, or that is nothing but the slip speed. So requirement is that we have to maintain this E1 by F1 constant. Okay. So how can we do that, or that we would come into that. However, if we can do that, what would happen? So the torque would be proportional to the slip speed. What does that mean? That means, let's say this is the torque and this is the speed. Let's write this rotor speed, and also consider that this is the load torque, let's say. So in that case, we would have the torque speed characteristics, something like this. Of course, not not a very new thing. If you remember, for the induction machine, the torque speed characteristics look like, let's say, the green line 1 or green line 2, anything. And that means, and for those cases, of course, this is the synchronous speed. Let me write ns1, and this is the synchronous speed 2. Okay. So if we start with the synchronous speed 1, the first the green line 1 would be the torque speed characteristics. If we start with the green line 2, or so let's say in synchronous speed 2, so in that case green line 2 would be the torque speed characteristics. Of course, over the top of that there would be the a bend like this, and the induction, the equivalent, the torque speed characteristics would continue like this. However, for this operation, or for this discussion, let's restrict ourselves into only the linear part. Now, if we move from the linear region, so let's say we reach this load torque using this synchronous speed. Now, once we reach this, and if there is a variation of the load torque requirement, or there we require further load torque, so in that case, if we reach the nonlinear part, we need to move for different synchronous speeds such that we can move there. Okay, so now by our discussion here, that the torque, the electromagnetic torque is proportional to the slip speed, you can see that means that the this torque, oops, would be proportional to the slip speed here and proportional to the slip speed here. So the slip speed required in this case to produce the torque would be given by the slip speed here and the slip speed here. Now, if you consider the load torques are same, so this slip speed value and this slip speed values are same. Now, go by the symmetry that this line is equals to this line because this gives the same, these are the same load torque, and further this line, this part is equals to this part because the torque being same, we have the same amount of slip speed required. So the two triangles that can be seen here, those are congruent to each other. So, and in a sense, we have the line, the green line 1 and green line 2, those would be parallel to each other. So if you want to, by using by keeping the E by F, the part in the third bracket constant, if you want to achieve different amount of different load torque, and for that, if you move from one synchronous speed to another synchronous speed, by that also happens, because to maintain E by F, this ratio, if you change the frequency, you change the voltage also, so that way you change the synchronous speed also. So this way all your torque speed characteristics move parallel to each other in the torque speed graph, or the torque speed this sort of plane. Okay. So if you plot the torque speed characteristics for this VYF control or variable voltage, variable frequency control, your torque speed characteristics at different speed or different synchronous speed should be parallel to each other this way. So we are actually moving from one synchronous speed to another synchronous speed by changing the frequency. And to maintain the E by F constant, we have to maintain the we have to, once we change the frequency, or we have to change the voltage, or if we change the voltage, we have to change correspondingly, we have to change the frequency also, such that we can maintain the E by F constant. Now what does this mean, what does this E by F mean, or this maintaining this ratio constant? Now this E1 by F1, if I let me add with this the some a few extra terms, that is twice pi into, let's say, Lm. Now this you can see here from the equivalent circuit, this is equals to the magnetizing current flowing through the this branch. This is the current, magnetizing current flowing through this branch. So this is nothing but the Im. And so if we keep the E1 by F1 constant, that means the magnetizing current remains constant, and that also means this is the source, or this is the cause of the flux through the induction motor, so the flux remains constant. So E by F or V by F, keeping V by F constant means keeping the flux constant. And usually this E by F is so maintained that the flux remains at its maximum or rated value. So we can get maximum amount of torque for the current. We would see later that if we keep the flux constant, so we can get maximum torque for a given amount of current. Now, how can we keep this E by F constant? Now, if you look here, E by F here is the induced EMF across the stator or the primary of the induction motor. So that is not accessible to us. So only way to keep this E1 by F1 constant, or maintaining this E1 voltage induced EMF, that is by maintaining the or changing the value of the voltage V1, which is the applied voltage across the stator. Now, if we use this circuit here, so equivalent circuit, so we have the current I1, and that current is flowing through this branch here, and due to that we can consider as if the voltage drop or produced across this across this uh, uh, magnetizing branch, that is responsible for producing the induced EMF E1 here. Now, for this discussion, let's neglect the value of the core loss resistance, because that is not the part which is of importance to us. Okay. Now, uh, we can write what is the ratio or what is the how E1 is related to voltage V1. So you can look here. E1 is equals to V1 into J omega. Okay. So we are interested about the ratio. Let's write this. This is equals to Lm divided by L1 plus Lm minus Jr1 by omega. Now, as you can see here, of course, if we try to maintain this induced EMF V1 by changing the value of V1, we would try to keep them as equal as possible, or there should be very negligible amount of differences. Now, this is of course this can be easily maintained if you consider that L1 is negligible compared to the value of Lm, the magnetizing reactance, and further that means we have the problem with the imaginary part here, that is the R1 by omega. Now, if you once again consider that omega is large, or this stator applied stator frequency is large, so in that case this R1 by omega, that would be negligible. So in that case we would be able to neglect this. So if we can neglect this should become Lm divided by, already we have neglected everything, so this should become equals to Lm. So we E1 can be maintained to be induced EMF can be maintained to be very almost equals to V1. So our job of controlling the voltage induced EMF by controlling the voltage V1, that would be easy. However, the problem comes when the omega or value is low, or the frequency is low. If omega is low, so that means there would be another part in the denominator which is added, or that because that is a complex part which would be added to this. So that means E1 would be greater than, magnitude wise E1 would be greater than V1. So we are applying a voltage, certain part of which is dropped across the resistance, stator resistance. So at low frequency, that means induced EMF, the induced EMF, what is happening inside, or which is our control variable, actually, or my theoretical control variable, and the voltage we are applying, that the can control voltage that is less than the applied voltage. Sorry, I made a mistake. This is here, this should be U1 is less than V1. So at low frequency, we have to maintain this induced EMF, and E1 almost equals to V1, or maintain this E1 constant, E1 by F1 constant. We need to raise the voltage little bit. So that is called the low frequency voltage boost. So at low frequency, we need to provide some sort of voltage boost. So if we plot the required value, or the required relationship for this, let's say this is the frequency axis, and this is the applied voltage V1. So in that case, normal requirement is that this should be the the voltage should be increased linearly. So such that if we can extend this should be like this. And further, once this achieves the rated voltage, the frequency is also the rated frequency, maintaining the ratio. So beyond that, we cannot increase the voltage. So the voltage should be, or voltage would remain constant, although the frequency changes. So if this happens, of course, we reach into something called the reduced flux operation. So as the voltage remains constant, however the frequency increases, so the flux goes on reducing. So that is also called the constant power region. Anyway, however, at lower frequencies, we cannot maintain the V by F ratio to be constant. To maintain the E by F ratio constant, we need something called voltage boost. So instead of starting at 0, we need this much amount of voltage boost to be provided at the starting to compensate for the drop across the stator resistance. Okay. So, and finally, the V by A by itself is current limited operation. If you remember the dual starting of the induction motor or the requirement for the starter of the induction motor, we require somehow the voltage is to be maintained low at the starting. Now, by using this V by F control or this variable voltage, variable frequency control, maintaining this V by F ratio constant, we can actually limit the current of the induction motor at the starting also. Let me write this way: the torque is taking the same expression we used earlier, twice by F1, and we have the I2 square R2 by S. I would keep this I2, one of the I2 as it is, and I would write this as I2 into R2 by S and further another I2. So this is equals to thrice P by twice F1 into I2 R2 by S. And further, let's use the expression for the current I2 in terms of the induced EMF. That is equals to R2 by S whole square. Now, once again, use the same expression or same condition here, that R2 by S whole square is much greater than this omega 1 L2 whole square. So in that case, the torque becomes into as F1. Okay. So now if we can maintain this E2 by F1 to be constant, of course, if we can maintain E1 by F1, the ratio to be constant, we can that is same as maintaining E2 by F1 constant. So in that case, you can see that the torque produced is proportional to the secondary rotor current. and the rotor current, as you that is more or less equals to the stator current. So in this case, the torque produced would be proportional to the stator current. So that means by using this, we can also indirectly or limit the current of the induction motor. So starting current for the V by F controlled induction motor would not be that high if you consider the case of dual starting. Okay, so usually that is of the order of maximum goes around two times, not 5 to 6 times that happens in case of the dual starting. So any confusion here, or I would move to the discussion of the on the procedure and the actual experiment. Okay, so if you have no confusion, I am happy. So, so this is the experiment showing you the or the manual showing you the details of the experiment. So, title, objects, and the circuit diagram. So, this is actually the experiment is done in open loop, although that does not make any sense from the practical point of view. However, for experiment point of view, that gives us some idea about the control, how that is done and or how to do that. So here we have the three-phase induction motor shown. Okay, so so here we have, this is the three-phase induction motor. Of course, this is driven by a power controller. This power controller, what this power controller does is, this power controller, this actually has a DC source, and then from the DC source, using an inverter, we can generate the variable voltage, variable frequency across the stator of the induction motor. Of course, without this, we cannot produce, without using this sort of an inverter, it would be difficult to produce the variable voltage and variable frequency. That is of course not possible at all possible from the grid supply, because the voltage and frequency is constant. You can change the voltage little bit by using, let's say, variac, because there is a problem in the change in the torque produced by the induction motor that way. Otherwise, of course, you don't have any way to change the frequency. So the induction motor, because we require some sort of loading to this and variable loading to this, that is connected to a DC generator, and the DC generator is connected to a load box. So now, if the DC generator generates some sort of electrical power, and the DC generator is loaded by the load box, and by using different amount of current, by using different amount of current drawn or the power drawn from the DC generator. Now this DC generator once loaded, that draws the mechanical power from the induction motor shaft. So that means this way we can indirectly load the induction motor mechanically, and further the load of the DC generator once changes, that changes the load to the induction motor. So that way we can have a variable mechanical load also, which is otherwise a little bit difficult. Okay. So now this, what is the variable voltage, variable frequency requirement? That is how to maintain the ratio and what should be the frequency, what should be the voltage. That is maintained by the control electronics at the which controls the inverter system. Now to the control electronics, we have the we can put the variable, we can usually put the requirement of the synchronous speed or the actual speed of the induction motor. So that way the control electronics usually calculates what should be the V by F ratio, and so and from that you can it calculates what should be the voltage that need to be applied from the inverter. So that way this dictates what should be the voltage, and frequency that is already dictated by the requirement for the speed of the induction motor. That way what is the speed of the synchronous speed of the induction motor. So using these two controls, we can generate the three-phase voltage reference to be applied across to be generated by the inverter, and that need to be applied across the induction motor stator. So this is the control. This is the power electronic circuit and the control circuit to control the applied variable voltage, variable frequency across the stator of the induction motor. Now, procedure run the three-phase induction motor at different voltage and frequencies at no load condition, starting from 5 hertz to 50 hertz in steps of 5 hertz. So you change the frequency in step of 5, 10, 15, 20, this way up to 50 hertz, and observe the V by F ratio. Of course, at lower speed, the ratio would not be maintained constant because of the requirement of the voltage boost at lower frequency. However, beyond certain frequency, usually you can say, my guess from my practical point of view, this should be around 15 hertz to 20 hertz, where the voltage boost requirement ends and the V by F becomes completely proportional to each other. Run the motor at different frequencies, we have 40 hertz, 40, 45 and 50 hertz, keeping V by F ratio constant. Load the motor at different capacity, take all the instrument reading. So that is the second part, where you run the motor at different only different frequencies, maintaining V by F ratio constant. Of course, this is at comparatively higher frequency. Thus, the V by F ratio would be maintained constant. Now you go on loading the induction motor, and you would see that that there will be very little change from the synchronous speed. Once again, maintaining and the torque would be proportional to the slip speed for these three cases. Okay. So if you plot the characteristics, you would see at different frequencies there would be torque speed characteristics of different of linear nature, and they would be parallel. They should be parallel to each other. Now, in the report part, comment on the V by F ratio obtained in run 1, specifically at low frequencies. Of course, we discussed that at lower frequency there would be certain voltage boost automatically automatically added by the controller. Otherwise, you have to do this. If you take out the controller, tabulate the reading obtained from run 2 and calculate torque in each case. Of course, that you have to calculate what is the load connected across the DC generator. So you have to multiply the voltage into current. So here the power electrical power would be voltage into current. You multiply that is the output of the generator. Now consider some sort of let's say constant efficiency of the generator. Let's say, so if we divide this by the constant efficiency, we would get the mechanical power input to the generator, and that is equals to the output power of the motor. Okay, so this way you get the output power of the induction motor which is required, and that the output power of the induction motor is the mechanical power. So P output mechanical divided by the rotational speed of the induction motor. That gives you the torque produced by the induction motor. So now plot the torque speed characteristics at different load on the same graph. Of course, that means these should be parallel to each other this way, what we discussed in the just before that, before this. Comment on the torque speed characteristics, so that is done. Plot the torque current characteristics. So torque should be once again torque should be proportional to the current here, because what by following what we already discussed. Plot frequency versus slip speed curve. This you have for this you have to calculate the you already have the idea about the synchronous speed, frequency, and you calculate what is the slip speed. So from that you calculate the frequency versus slip speed characteristics. So at any given frequency, the slip speed should remain constant. So that was about the whole procedure of the experiment. Now, if you have any question, you can ask me. Otherwise, we would move towards the end of this class. Okay. So, so thankfully everyone understood everything. No question here. And I would send you the data for this experiment by I hope by tomorrow evening, and you would get 7 days after I send you the data to submit the lab report. Okay. So and I would provide you the link to submit the lab report also. And I hope because you have performed a few labs, offline labs, I hope you know how to prepare the lab report. In case of any confusion, you can call me anytime.
Okay, sir. Thank you.